Okay. Yeah, first I would like to thank the organizers for inviting me, and of course I would like to thank the audience for sticking around past 5 p.m. And so what I'm going to talk about is about kinetic theory, about how gas kinetic theory can be applied to the sometimes exotic interactions of active particles. Yeah, so this is my collaborator who is now in Dresden at the Max Planck Institute, and I'm still in North Dakota. Okay, when I first got interested in active systems several years ago, I wanted to start understanding the simplest, what I perceived as the simple system, that it's flocking, because the degrees of freedom is less, for instance, than understanding actins and motors. So I'm interested in this collective coherent motion of self-propelled particles, which can be birds, fish, or bacteria. So here's a picture of flocks of such animals. And my goal is to set up a theory of the phase transition to collective motion, one of my goals. And what's usually done, as I've seen in many talks, is one cooks up some hydrodynamic equations using symmetry considerations, so like in the Turner 2 theory. There's nothing wrong with it, of course, but I'm interested in the quantitative kinetic theory based on based on the microscopic details, so where I actually can derive these equations. That's the goal. Because often you have very many transport coefficients in these equations, and you don't know how they're all related to the, the underlying microscopic parameters. So, yeah, that's what I'm trying to do. Well, that's how I started out. Yeah, so you probably have all seen that simple flocking model by Thomas Wischek from 1995. And when I first started looking at these things, there wasn't really a theory for that model. I mean, a quantitative theory for that model. Of course, there was generic theories which described phenomena qualitatively. And anyway, so that's what I started out with. So for those who don't know it, it's a two-dimensional model where we have n particles which always have a constant speed v0. So all they do is just moving around and turning their flying direction. So they are changing that angle theta. So n is the labeling the particle number. Yeah, and then it's a simple two-step dynamics. There's a streaming and a collision step. So in the streaming step, the particles are just changing their position. So they do a ballistic move according to their velocity vn. And there's a time step tau, which can be arbitrary in this model. So it can be also very large. So I'm not trying to discretize a continuum description. Okay, so now the collision step, it's where they start interacting, where they change their angles. And it's also very simple. For instance, if you focus on this yellow particle here, which is flying in this direction, then we look in a circle of radius r around that yellow particle and find all the neighbors. So in this case, these 3 white particles. And then we calculate the mean direction of all 4 particles. And that's done by just adding up these 4 vectors, which gives you a vector pointing here. And then you take that angle, call it theta bar, and that's the mean angle. And then you add some noise, which models, for instance, that the particle doesn't want to go in the mean direction, or that there is external influences, so it cannot follow that mean direction. And here... Pardon?
Not memory?
Well, not in this model, no. That noise is completely uncorrelated for every particle and also in time. It's just in the computer you just draw a random number distributed equally between eta over 2, minus eta over 2 and eta over 2, and where eta parameterizes the noise strength. So that's that original Wischek model, and the particles are point particles. Okay. Yeah, if you don't like it, I mean, it was Wischek who set it up. Okay, so you put this n particles, usually a few thousand on the computer, periodic boundary conditions, and you start simulating that. And then what you will see, well, let's just talk about another version of that model, which is called the metric-free or the topological Wischek model, because several years ago, people studied flocks of starlings, and they found out that these starlings, they don't look at the fixed radius to orient themselves, but they look at their, let's say, 5 nearest neighbors and follow what they are doing. And if the density is very low here, like in this picture, these 5 neighbors will be quite far away, and in a dense, if there's a dense spot in the system, these 5 particles will be very close. So that it's an actual interaction which with a variable range. So it's not a fixed radius anymore, but the number of neighbors is fixed in this model. And you might think it's a tiny change, but it actually has qualitative implications, which I will talk about later. Okay, so these are the 2 models. And here it's back to the original Vishek model. It's this simulation in a small system. And then you see this phase transition. It's not completely sharp because we are in a small system with a few thousand particles. And what you do here is you measure that order parameter omega, which is pretty simple to understand. I mean, you just add the velocity vectors of all particles, and if they're all aligned, you get a very long vector. And you take that length and normalize it in such a way that if they are perfectly aligned, that omega will become 1. And that's the case if the noise is very small, or is 0. And then for a large noise, so that means the particle really doesn't agree with its neighbors, it just picks more or less a totally random angle, then these little velocity vectors, they point in all different directions, so they look like a freely joined chain. And then the length of that vector will be very small, and then the order parameter is small. It's not exactly 0, it only goes to 0 for infinite particle number. Okay. Yeah, and then the big surprise, well, at least at the time, was, and that probably prompted your work, is that you see a long-range order even in a 2-dimensional system. And we know in 2 dimensions, in an equilibrium system, that that's forbidden by the Mermin-Wagner theorem, where the long-range order is destroyed by spin wave fluctuations. Because if you take that Vishek model and you freeze the particle, it means set the velocities to exactly 0, then you have like a disordered XY model, and then there can be no long-range order. But as soon as you switch on the speed, you're in that other, apparently in that other universality class, and you get order. Yeah, and that's because we're non-equilibrium, because these agents consume energy to maintain a constant speed, and their velocities do not equilibrate when they collide. Yeah, they also exchange momentum with the environment. So if you just take the particles and calculate their momentum, that will not be conserved because it's constantly exchanging momentum with the environment, which is not part of the model. Yeah, so let's start now with my theoretical approach. It's I think, different from what most people do, because I start out with the discrete model, discrete in time, because my goal is I really want to fit the Vishek model, because that allows direct one-to-one comparisons with simulations and theory. So I'm, in a way, take the opposite approach than what John Tono did, not looking for generic features, but looking for a very specific model and trying to figure it all out. So here is I start out in a phase space. So let's say A is a microscopic state of the system, which is specified by the position of all particles, x1 to xn, and all the flying angles. So if I have n particles, I have 3n degrees of freedom, which I will send to infinity at the end of the calculation. So that's a microscopic state, and here at time t, there's a certain probability for these states, which I just assume. And then there will be a transition probability which hides all the nasty physics, all the collision rules, and that describes how I actually get the probability for another microscopic state B at the time t plus tau. Okay, so this is a Markov chain, and yeah, and WAB is the transition probability from state A to B. So what I do here is a hopping in phase space. And yeah, so that's the starting point. And of course, the physics is here in that transition probability. How do I get from A to B? And it's a product of delta functions, which are also periodically continued, because the angle periodic. And what it's encoding here is that's just the peak or contribution to the transition probability if the post-collisional angle theta of a particle I is equal to the average angle of the neighbors plus the noise. So that's all what's in here. And this average angle then will depend on position and velocity of the neighbors and so on. So it still looks simple, but it's not, because there's a lot of dependencies hidden in that theta bar. Yeah, so you have the product of that, and then you have the average over the noise distribution, because remember, every particle has its own noise source. So that's why there is an n-dimensional integral. Yeah. Okay. So problem with all of these things is that they are exact but not tractable unless you do some drastic approximations. But at least they're controlled approximations. Yeah, so that's the equation just written now in terms of that probability, of the n particle probability. And I have to integrate here over all the pre-collisional angles, because this thing here depends on theta, and so I have to get rid of these theta bars. Yeah, again, that's that Markov chain, and now I have the streaming in here, that streaming step you see here with the time step tau multiplying the velocity. Yeah. Okay. So now let's come to the approximations. I want to reduce this to a one-particle description. And to do that, I need that molecular chaos assumption, the same assumption needed to derive the Boltzmann equation. And here it's very simple. It's just, I take this n particle probability and write it as a product of the one particle probabilities. And what that means is that I assume that the particles are statistically independent before a collision. So there is no pre-collisional correlations. And then this whole thing factorizes.
So are those supposed to be 2's in the second one there?
No, it's the one particle. Oh, yeah, you're right, yeah, sorry. Yeah. So what I end up with is a kind of a mean field treatment. It's dynamic, and yeah, this assumption is actually never true unless you're in infinite dimensions. And here it's actually pretty good if the particle streams very far compared to the radius of the interaction, because then you have a very good mixing. The particles who meet in a cell have never seen each other before, or if they have seen each other, they forgot about it. Okay, so the noise shouldn't be too small, and that velocity or the time step should be large. So it's kind of the opposite limit what people use in the simulations.
So you can't be too close to a perfectly ordered state for this approximation.
Perfectly, pardon?
Well, if you had a perfectly ordered state, even no matter how fast the particles move, they're always going to see the same neighbors because they're all going in the same direction.
You can still make the velocity extremely large, and then there's still a little noise. But it's getting worse and worse.
There's an order of limits question there, right?
Yeah.
For a given noise, there's a lower limit on the
There is a certain range, yeah, that's true. But nevertheless, we can just use it. And, okay, sorry, I forgot something. Here, you still have that n particle probability, and to boil it down, you multiply with what's called the one particle phase space density. So it's a product of delta functions where you introduce a field variable. So you look at a fixed point x, and then you just sit there and wait for particles which end up there and have the right direction theta you want. And if that's the case, you count it. Yeah.
Does the molecular chaos assumption means you can't connect to equilibrium because they have to move with a certain velocity for a certain level of noise in order for that assumption to be good?
Well,
they can't stay at a place because...
Yeah, they never really, I mean, they always have a constant speed, right? But they have to move very fast. Yeah, they can't stay at the same spot. That's true. I mean,
they would have to if it were equilibrium, right?
Well, it's an intrinsically non-equilibrium system. I mean,
Right. So I'm talking about the equilibrium limit in which you would go there. So.
Well, I go to a stationary state, yeah, where they assume a certain profile, or they're totally homogeneous and pick a certain mean direction or something. That's the limit, yeah. Yeah. Okay, so I take this phase space density. I think that was in your talk too. And then you multiply the whole equation with that, and then you integrate out all the positions and all the angles, and use that molecular chaos assumption. If you do that, then you end up what I call an N-Skok type equation, because it's neither a real Boltzmann equation nor a real N-Skok equation, but it has some properties of an N-Skok equation. So, yeah. And so on the left-hand side, you have now, instead of the probability to find a specific particle at a certain spot, you have this number density. So number density of particles with a given angle at a given position. And that's kind of the ensemble average of that phase space density. So this is the full phase space density, and I average that, and I get this F. So like in the Boltzmann equation, you have this function, and then on the right-hand side you have a nasty collision operator, and you will see that it's non-local and non-linear and has a lot of nasty features. And that's usually when I talk about in front of undergrads, as an American professor, I always put in disclaimers.
You're in England now, you didn't need that.
Yeah, sorry. But I got used to it. Okay, so that's the collision operator. I'm not going to explain in all detail, but you will see. Yeah, it has a singular kernel, delta function. It has a product of these f's, so it's nonlinear. Then it's non-local in space because you have to integrate the positions of, let's say, particle 2 and 3 around that position where the particle 1 is fixed. So that's that Enskog-like feature. Yeah, and then also you have a weight here, which turns out to be a Poisson weight. So in a way, that thing already considers Poisson fluctuations like of an ideal gas. Anyway, and then you have a sum over all the possibilities. For instance, this particle can be alone, no partners. Then that will be the n equals 1 term that occurs with a certain probability. Then it can have 2 partners, would be n equals 3, and that all occurs with certain probabilities. And these are point particles. So you even can have all particles in that circle, right? So it's actually valid at arbitrary density. So I'm not really limited like in a real gas by high densities. But that's kind of artificial because these are point particles.
You're not really limited if you can do the sum.
I can do the sum, yeah. Well, let's show that. Anyway, now one starts out with looking for the fixed points of that collision operator, and you will find 2 main solutions. First, it's a constant. F will be constant. That means the probability to go in any direction is the same. So that's the so-called disordered state. And then you can also find a symmetry-broken state with an arbitrary direction, which is preferred. And that occurs below a certain critical value. And yeah, so that's what one can do. And
those are homogeneous?
yeah. For now, I just kept everything homogeneous. Yeah, and then you get this phase diagram. So M is a measure of the density. What M is the average number of particles in a circle. So it's like the average number of interaction partners proportional to density. And then, for instance, here, if M equals 2, then you can calculate the critical noise, which is around 3. If you're below, then you're in the ordered state. And if the noise is larger than that, you're in the disordered state. So my curve is that solid line. Then there was some older numerics by several groups. And then we also did our own numerics. These are the open squares. These are I think that these are simulations at relatively large velocity. That's why I got a pretty good agreement. If you go to small velocities, the critical point actually drops down by a factor of 2. But then I'm in the limit. My assumption is not correct. Okay, so that's yeah.
Is the theoretical curve a simple function? Is it just something like a to c is the power of n?
It's a square root. Yeah, like mean field. And then the square root actually, that's the square root here, that dash dotted. Yeah, it's more complicated. But it actually goes to 2 pi, meaning if you have an extremely high density, then even if you have almost 2 pi noise, you still can have order, because all these things, all these particles add together, and then they still can agree on a direction. Okay, and then what I did was I wanted to derive these equations you postulated, and I did a Chapman-Enskog expansion. So I define 2 order parameters here, density and momentum density, because Turner 2 theory has these 2 variables. So these are the zeroth moment of F and the first moment of F. And then I do this expansion with the power counting or non-uniformity parameter epsilon, which I set to 1 at the end of the thing. So every gradient gets 1 epsilon. So it's kind of a gradient expansion. Then time scales have to be scaled with epsilon also. Then the F and the collision operator have to be expanded in that. And then you start a horrible machinery. And in the middle, you see these integrals here. And since two days ago, somebody, embarrassed us with an integral, I'm going to ask you whether we have any idea about this integral if n goes to infinity. So the dimension goes to infinity, and you have this average angle, which is the argument of the sum of these phases, and then you multiply this by cosine of one of the angles. So anyway, I could do that, but then if you become more general, that means you multiply this by k, and here you put in more cosine factors. I got lost. So if anybody has an idea, that integral is just 16, like this. So it goes as 1 over square root of n. But our integrals are 1 over n or 1 over n to the power of 3, 2, and yeah. And also the modes in here, there are certain sum rules, and I don't know. We solved that numerically, but we need some help at this point here. Okay, and then this is the Turner 2 model. They have the continuity equation. And then you have this momentum equation, which has now 3 different convective terms, because it's not a Galilean invariant model. Yeah, and I wrote down trust is good, control is better, because I wanted to derive all these terms and see where I really find all of them. I did, at least the ones up to 3rd order, because my expansion was to 3rd order. But then I found a few new terms, and we're still discussing whether they're new or not. They look like this, for instance. So in the equation for the x component of the momentum density, or of this macroscopic velocity, you have such a strange combination. Second derivative of the density multiplied by the velocity, and here you have a mixed derivative. And surprisingly, that's rotational invariant. I got it out of for a tensor multiplying a vector, so I knew it would be a vector again. But I don't know, probably hard to guess. And there's more terms which I haven't analyzed yet. The reason why I didn't analyze that stuff is because it all became unstable. So first I did a stability analysis. So everything was perturbed, density and momentum with a small perturbation of wavelength lambda. And then near that threshold, that means if I'm in that ordered phase, close to where it breaks down and becomes disordered, there's a long wavelength instability. And I'm not the first one who has seen that. I mean, Bertin people have done that too. They get similar instability. But in addition, what I found is when I put these equations on the computer, and in that regime where it's linearly unstable, it also is non-linearly unstable. So everything really exploded. It's like a sound wave which becomes larger and larger, and then computer crashes. Yeah.
Doesn't that depend on what non-linearities you include?
Yeah, but that's what I first thought. Okay, maybe I need a 4th order, 5th order. Maybe that's a nicer nonlinearity. But up to 3rd order, I put in all the coefficients I calculated. I derived.
What usually happens when you add more and more nonlinear terms, you reduce the region of attraction. So you make approximation more accurate near the origin of the threshold, but less stable.
Yeah, that's true. I had to assume that I'm very close to the threshold. Yeah, but nevertheless, the other group, Bertin, who also has a similar equation, didn't happen in their approach. They ended up with finite solitons. So I was disturbed. But on the other hand, for that metric free model, we could show, and also the same group showed that there is no instability. So that little change of making the interaction radius have a variable radius was important. Okay, after I saw that everything was unstable, and here you see why. You get like a big density wave. Again, I'm not the first one who saw that. It's just the high density here, and then it's kind of a disordered phase in front. And these density waves have large gradients, so I figured, well, I do a gradient expansion, so it could be that higher order gradients are getting worse and worse, getting more and more important, so that everything would break down. Even if I would spend a year and derive the 4th order term, it probably still breaks. So I didn't even bother with that. And And I thought, well, you have to sum the gradient terms to all orders. Then you don't have to worry about this anymore because the hydrodynamic description breaks down, possibly because of these small gradients. It was just an assumption. And then in practice, I just say, well, let's not even deal with hydrodynamics anymore. I just go back to the kinetic equations and solve them numerically, because then I didn't have to make any gradient assumptions.
Thomas, I just want to clarify. You don't see the instability for all values of parameters, it's just near the transition, right?
Yeah, but the problem was even when I went to null noise in the ordered phase, it was still unstable. But there, my
So you're saying it's unstable for all values?
no, you can trust that approach if you're far away from the transition point, because you need more.
Because you truncate it.
Yeah, I truncate these Fourier modes. Yeah, but I just couldn't find any stabilization if I make the system large enough. Yeah, so I forgot about it, and that's why I didn't look at all these terms and just put this on a computer and solved it like people solve a lattice-Boltzmann equation. Only problem is here, I have to look in all the different directions, so I won't end up on a lattice side like in lattice-Boltzmann. But I did some interpolation, and I used like 1,000 different directions. So the good thing is that the speed of that is constant, so I just have to go around in a circle and scan all the points there. And that actually worked out very nicely. I got such an invasion wave. So this is the density, and that wave grows to the right, and it's actually completely unperturbed if you go in that direction. It's like a straight front growing, and that grows at like 90% of the maximum speed, and that's actually larger than the speed of sound in the disordered phase here, which is about 71% of the particle speed. And then what I found, and that was, I surprised Hugues with that, that this shape of that wave, because he saw all these waves before me, but the shape of the wave actually can be scaled, and because its height is proportional to the square of the system, of the length of that channel here, and its width is proportional to 1 over the square of that channel. So it's very strange. And then people ask me, so how many particles are actually in that wave? Is it a constant number? And it looks like that it's always half of the particles are in the wave, and the half is in the back, half of the particles are in the background. But that might depend on some parameters. I didn't explore whole phase space. But I could scale, you see, 300 to 450. I could scale that onto one curve. And then again, people still didn't believe it. And then I did my own Vishek model simulations, and that's that fuzzy line. And you see it's quantitative, it agrees quantitatively. Of course, there's still a debate. Is this, is it always a one band or two bands? And yes, there is regions where we have more than one band. But nevertheless, that thing exists, and it has that kind of unique shape and that weird scaling. Of course, you might ask, what happens if I go to infinite length? Would I get infinitely high wave with infinite pressure? So again, there was a discussion that it probably breaks down, but we don't know why and when. Yeah.
Setting the density in the far field?
That's the funny thing. The density in the far field adjusts to half of the average density. So that wave is it kind of dominates the whole system. It changes everything. Also, because of periodic boundary conditions, so it goes through and through like hundreds of times, and then everything gets changed and adapted. And yeah, so that's that wave. Sorry. Yeah, and then you also see if you have that soliton state, you get that the phase transition now of the order parameter looks like first order. You have a jump here and a hysteresis, which becomes pretty large if you go to large systems. So I call it that the invasion wave induces a first order phase transition.
Hold on. Why do you have a region labeled homogeneous state? I thought you said it's always stable.
Or if the system is small. If you go below the critical wavelength, then you get, yeah. Okay. Yeah, and then I send two solitons against each other, and then they survive, so they tunnel through each other, just adapt their height a little bit. So it has some soliton-like properties. So here it's the low time, and then later you see these other plots here where they tunnel through each other. And then I'm quickly going to say what I did going beyond mean field. So I treat now. I have now two coupled kinetic equations, one for F and one for the two-particle correlation function. I do a cluster expansion of that n-particle function, neglecting three-particle correlations, which is probably not a good idea, but I have to start somewhere. And well, then you get horrible integrals of this type, all these products where you have the two-particle function and you have the Fs. And then I had to find a way to treat them and to memorize them, and I use these diagrams. So in the two-particle function, you fix 2 points, and then every point has its radius of interaction, and there can be other particles which mediate correlations, and these links here are functions, the G functions, and dots are F functions. So it's just a way to write down all these integrals without using too much paper. Okay, so that's basically it, and that's still work in progress. This shows horrible instabilities. Here's my summary. So I developed this kinetic theory just for the V-shaped model without going to continuous time. Just kept everything the way it was in the original model. Then I found these continuum equations, and actually I have 17 transport coefficients. They might be related somehow, but anyway, I just wrote them down. Then I found this soliton-like wave, which actually is in quantitative agreement with direct simulations, and it shows that strange scaling. Yeah, and then I showed that the invasion waves provide one mechanism to make this flocking transition discontinuous, but there might be more mechanisms. Okay, that's all.
Thank you very much. So we were spared the sex life of the amoebas, but not the collision integrals. Coming up to bring it over.
Okay, so I just want to maybe for you to comment on something. I mean, do you have any idea what the difference between using continuum versus discrete time will do to this sort of analysis?
Well, I had a discussion with Bertin, who did it in discrete continuous time, and he said, well, what you do is basically just including higher density, so you can deal with 3-particle, 4-particle collisions. And I agreed with him first, but then I looked at the limit of binary collisions, and then he got a different phase diagram. His phase diagram was dependent on the velocity, and mine wasn't. So seems to be, but he then said that it's not a one-to-one model for the V-shaped model. It's just a model for the for a self-propelled particle. It's not exactly the same.
But you're also making different approximations than he is, right?
Not really, because by writing down the Boltzmann equation, you can only do that if there's molecular chaos. So in a way, by writing that down, he already forgets about the correlations. Yeah. So.
Related question, I guess. I mean, I had the impression that Bertin and company have a soliton solution which is different from the one you find.
Yeah.
Have you any idea what the origin of the difference is? Yours actually is something that in the infinite size limit either goes to something singular or doesn't exist, right?
Yeah. No, that's true. I saw that also. Yes, solitons, he gets it from the hydrodynamic theory.
Yeah.
But he said something that the height is limited, but
yeah.
he wants to have another look. So.
The approximation is different. You obtain internal expansion, which not is the same.
So,
Quite sensitive to expansion.
so there seem to be 2 microscopic length scales in your formulation. One was the range of interaction, the other the mean free path.
Right.
And so the Chapman and Skog expansion is limited by the larger of the 2. Is that right?
No, yeah, Chapman and Skog
epsilon
expansion
should be.
it's an expansion in the Knudsen number. That means how the larger of the 2 relates to the length scale of a perturbation. So you can still make a very smooth, long wavelength perturbation, and then you can do the Chapman and Skog.
So if you go to the continuum limit, time limit, then you would need to keep the quantity u tau finite.
Which quantity?
The velocity times the elementary discrete time step that you have.
In a way, yeah. That's, yeah, because that was the assumption for the earlier approximation. Yeah.
It's known that the Chapman-Enskog expansion for the Boltzmann equation is stable at the Navier-Stokes order and unstable at the next order. There are some who've diagnosed that as due to a Taylor series assumption and who've tried to tackle it by rational approximation. So Marshall Slemrod in Wisconsin, for example. So I wonder if you've tried other non-Chapman-Enskog expansions to try and get rid of the instability.
Yeah, you know, I've seen that too. That you know, it's one of these asymptotic expansions. You cannot go to higher order. But this was horrible enough, so I had no intention to continue.
So this was not going to higher order. It was rational function expansion and not polynomial.
Yeah, but still more difficult, I guess.
So, Thomas, this is a question I should have asked you 2 weeks ago, but when you can derive all the parameters in the hydrodynamic theory, so in particular you can derive the compressibility.
Yeah,
And do you get a finite compressibility?
I didn't look at all of them, but I would guess, yeah, because what stops them from compressing?
No, I mean,
Oh, you mean
what I mean is, do you get a pressure that grows when the density grows?
Yeah.
So it's a little tough to understand how in a system where the pressure grows when the density grows, you can make solitons whose density grows like the length of the system to the 4th power. And those just keep going.
Yeah, well, my easy answer is...
You would think at some point the pressure force would start to play a big role, right?
Yeah, yeah. But it agrees with simulations, and I also don't understand it. Yeah.
Is group breakup anywhere close to this, or would it be an instability that you would get 2 peaks, or you wouldn't have a hope of getting
That's
group?
actually what I was asked to look at, because Ukshatei did simulation just a week ago, where he sees that that peak breaks up into 2. And it looks like a nucleation process, but he found also a window where the 1 peak solution is fine.
Okay.
So, but it becomes smaller and smaller, that window, if you make the system larger.
I think Len said if we don't get out, they will lock us in. Yes?
I think it's easy to get out.
Okay.
It's not easy to get back in.
Very good. Okay. Well, let's thank all the speakers. It was a nice afternoon.
You can use the other